Hello everyone, I'm going to walk you through today I'm going to walk you through the three key techniques we use in our class to find the volume of solid: the disk and washer method, the shell method, and the method of like cross sections. I'll do one full worked out example for each one step by step, so you can see exactly how to like set them up and solve these problems on the upcoming exams. So every technique we covered today boils down to the same formula. Volume equals the integral of this cross-sectional area A of x over the interval. The three methods are really just three different ways to figure out what that area functions of A of x looks like depending on how the solid is built. So first let's start with the disk and washer method. The distant washer method is what you use when a flat region is spun around a line to create a solid, and each like small slice perpendicular to the axis is a circle. If the region touches the axis, you get like a solid disk, and if there's a gap between the region and the axis, you get a washer, a circle with like a small hole. And you subtract that inner radius squared from the outer radius squared. The key formula is basically V equals pi times the integral of r squared, or r squared minus r squared for a washer. Here's our first example. We're revolving around the region between y equals x and y equals x squared on the interval from 0 to 1 around the x-axis. Since the line is above the parabola on this interval and the region doesn't touch the axis anywhere, we get a washer and not a solid disk. The outer radius is x and the inner radius is x squared, so we set up V equals pi times the integral from 0 to 1 of x squared minus x squared dx. Don't forget the dx. Now we just grind through the algebra, squaring squaring x squared gives x to the fourth, so we integrate x squared minus x to the fourth from 0 to 1. The antiderivative of x is The antiderivative of x squared is over 3. Antiderivative of x cubed over 3x to the fifth over 5. Plugging in 1/3 minus 1/5 and plugging in 0 gives 0. 1/3 minus 1/5 is 5/15 minus 3/15, which is 2/15. So our final volume is 2 pi over 15 cubic units. And that's method one from start to finish. Now we move on to the shell method, which is your go-to when the disk or washer setup gets like a little kind of funky. Usually because you have to solve for x in terms of y instead of slicing perpendicular to the axis of revolution. We slice parallel to it, creating a series of nested cylindrical shells like tree rings basically. Each cell has like a radius, a height, and a thin thickness dx. The formula is V equals 2 pi times the integral of x times h of x dx, where x is the radius and h of x is the height of that shell. So for our second example, the region under y equals x squared from x equals 0 to x equals 2, and it's revolve about the y-axis. If we try this or washer here, we'll need to rewrite the parabola as x squared root of y, which adds an extra step, which even I don't want to do that. With shells, we can integrate an x directly. Each shell has a radius x and a height x squared, so the volume is 2 pi times the integral from 0 to 2 of x times x squared dx, which simplifies to 2 pi times the integral of x cubed dx. Then we multiplying x by x squared. Oh yeah, for method 2, we're multiplying x by x squared, which gives us x cubed. So we need the integral of x cubed from 0 to 2. The antiderivative is x to the fourth over 4. Plugging in 2 gives 16 over 4. which is 4, and plug in a 0 gives 0. So we have 2 pi times 4, which is 8 pi, and that's our volume using the shell method. Third method is different from the first two because there's no revolution at all. Instead, we're told the base of the solid is some flat region, and every cross-section perpendicular to that to an axis is specific known shape like square or semicircle, or an equilateral triangle. The general formula is still v equals the integral of a of x dx, but now a of x comes from geometric formula, side squared for a square, or 1/2 pi r squared for a semicircle. Using a side length radius, we find the base region. Our final example has no revolution at all. Instead, the base of the solid is a circle of radius 2, and every slice perpendicular to the x-axis is squared. At a given x, the circle tells us y equals square root of 4 minus x squared. And since the square spans from negative y to positive y, the side length is 2 times that square root. So the area of each squared is the side length squared, which gives us 4 times the quantity 4 minus x squared. We integrate that from negative 2 to 2, since that's the full width of the circular base. Moving on, we expand 4 times the quantity 4 minus x squared gives 16x 4x squared. So basically, this is just a way. I'm just like going through this one by one. As a way for you to like see how it's done. But ultimately, it just boils down to 128 over 3 cubic units. So basically, how do you know which method to do when you're like doing an exam? The way is you can know is that if the problem describes a region being revolved and is easy to slice perpendicular to the axis, use a disk or washer method. If it is revolved but solving for one variable in terms of the other, which is a pain, switch to shells. If there's no revolution at all, the problem just hands you a base and tells you the cross sections are square, triangle, or semicircles. Go straight to the cross section method. Also, if you were to use all three, if you were to use like sometimes, I guess, all these three methods, you would get different answers. You would get different answers depending on the different types of methods you use. So basically, in conclusion, every one of these problems is really just b equals the integral of a of x dx, and we're just tweaking around with the formula a bit to find different volumes depending on like the axis of revolution. Discs and washer slice perpendicular to the axis of rotation. Shell slice parallel to the axis, which saves you from solving the other variables. And known cross sections skip revolution entirely and use whatever shape the problem hands you. I hope like walking through these examples helps you study for the final or any upcoming test. So,